So, hi, a little bit about me. I'm an engineer and a product builder. I have worked extensively in free open source technologies and platforms. I mainly use Linux at work. And I spent 13 years working mainly in embedded development for automotive, connected devices, e-mobility, like e-bikes and scooters. I've worked in many greenfields projects where they start with really big ambition for feature set and delivering a huge amount of features and best impact and being disruptive. But in many of these projects comes an approach, a deadline and delivery and release time, and suddenly these features and ambition is not very stable, and bugs keep coming. And I'm very sure some of you have experienced that in some of your projects. And when that happens, some of these features that gets reduced down, but the worst thing happens also is cybersecurity takes a backseat and gets deprioritized. So today's talk, it will be about how do we get a good foundation for cybersecurity for projects in general, how to weave it inside your project, so it is accounted for from day one, and it's not something that you get surprised by at the end of the project and try to bolt it on at the end of the project and it doesn't work. So today, embedded systems, they have increased in complexity, and most of the products today are extremely connected, meaning they become a distributed systems of multiple parts that they have to connect to each other. So you have in-field devices running on microcontrollers or SoCs. They connect to clouds. You have applications or companion apps on mobile phone. You have web portal for management of these devices. And this increase in connectivity and complexity, it also increases the attack surface that devices have today. And this increase in attack surface, it becomes designed in the product and by choice. This sudden tick in connected devices, it has been coined as software-defined products, where if you buy a product today, you don't expect it to be the same value you buy it at. You expect it to add value via firmware updates and software rollout updates. Customers expect nowadays when they buy a product that they receive security updates for many releases. They get a promise from companies that the feature set will grow and they will continue getting updates and releases. But this also changes the OEM's perspective on product release and shipping, where they can ship some limited minimal feature set, some basic security, and they can count on updating it later. Speed is very important for startups nowadays. If they miss a launch window, it can kill a product, it can kill a company, and they have a very limited budget from their investors, so it's not really an option to do the best cybersecurity you can, build it first and release it. You have to really understand how speed is very important for this company. So the priorities for an OEM is to ship on time, to reach the market really fast before competition does. So have any of us have bought a product before and started it for first time for out-of-box experience and got notification for update is now mandatory, or you have to wait until it updates? Exactly. I bet everyone have experienced that. And the reason for it is all the companies now, they have to wait until shipping date, work hard on the software all the way until the device comes into your hand to cover up bug fixes and security at the last minute. this is the current project reality we have today. It's like a game, tug of war, where on the left side you have engineering and security trying to do a really good TAR analysis to come up with all the threats they identify, all the security mitigations they need to implement. And on the right side, you have the business reality where you're limited with a feature pressures that have money impact. What adds the value to the customer, a deadline for launching the product, and a budget that they are constrained with. And there is no winning side here. Both sides are right about what they need and the requirement. And eventually, someone has to compromise and something has to give. And usually, cybersecurity also is one of the things that gets thrown out of the window first. And the product launch sometimes at acceptable reduced risk level, sometimes it's lagging behind. So it's something that you have to deal with in project reality. So the trend here is to shift toward mentality to security, that it becomes a marathon and not sprint. It means you can't do the most secure system for embedded nowadays at lunchtime. You have to set the foundation right and keep increasing and increasing the security. And you have to think about how can we reduce the risk to acceptable level before we ship, and go for defense in depth or add extra mitigation and extra level of security as the product develops and grows. So today's talk, I want to create a serious talk, and cybersecurity is a really big topic, so I wanted it to be a serious talk where we can talk about how to protect our products and the data in these products in various states. So data in transit, it means when data flowing in and out of your product. Data at rest, it means when the data is resting in your product, stored in the storage or in memory. And data in use means when your processes start pulling this data to read them, write them, and decide a business logic based on them. And there is also an important aspect in cybersecurity, which is how do we manage crypto keys and certificates and key infrastructure to provision crypto in our devices. So these are topics for a serious talk. It won't never fit in like 40 minutes talk. So we have today to focus only in data in transit, and we'll try to get a slot in upcoming years for the rest of the talk. So today's talk is, we're going to focus on how do we approach network security, since that's where data flows in and out of our product. And to do this, we will look into discovery, so we're going to have to think about how do we think about a product, what is the data in it, what is the endpoints in it, how do we protect that. And we're going to look into what is the right mechanism to protect the data flowing in and out of the product in these states. And at the end, we also will look into an example use case project. So I thought of a good embedded use case to come up with an EV charger, and we try to architect it together and look into how do we protect the data in it. So the first thing you do when you approach a cybersecurity in a project, you should be in contact with the architect of the product from day one. So you understand and you analyze the product from day one. And you need to really understand what is the data and the endpoints in the product. Where are they coming from? Where are they going out of the product? Is this data sensitive? Who owns it? And you need to understand also what is your CPU, network, and memory endpoints for the product. So if you have a server or if you have an ECU and it receives data, you need to understand that this data will be processed and having a huge amount of data is limited as well, and make it not available. You need also to understand what is your mission critical resources. So if you're in a factory or a food processing or water treatment plant, you need to understand some of these are very sensitive mission critical resources that you need to consider. And you need also to think what is the damage scenario if any of these resources gets compromised. And what is the impact and what is the severity of it. And if there is an attack path to that attack is possible, so if it's feasible or not. And what you do in this, you start a big Excel sheet and you list all of it as each one of it as a risk item that you need to work on. So this is basically how threat analysis and risk management work in a product, where you identify your items or attack surfaces, data, endpoints, resources, and you start building a threat analysis around them. How do we protect them? Who owns them? And what kind of mitigation that we can say we can use to reduce the risk level on these items. So when you build this model, you will start understanding what is the risk with it. And the second thing you should think about is how do we secure the network that this data flows in and out of the device. And a good network design, it relies on three parts. Controllability, you need to be able to control where the data moves, so who talks to who and where this data coming from and where it is going. You need also to have a visibility if any of this data deviates from the path that you were deterministic about. You need to have it logged and monitored and alert you. You also need a containment of failure. So if you have an exposed asset, you can't expose the rest of the data, or you can't expose the rest of the endpoints or the rest of the machinery if one of them gets attacked. So you have to contain the damage and reduce the blast radius if it gets exposed. Architects really like analogies, so I thought a little bit of analogy here. So the small castle in the picture is where the king stays, and for me an endpoint or a data is a king. So if you look into a picture of a city, you don't have someone that comes out of the street and just go meet the king or attempt to assassinate him directly. He has to pass through a secure steps on the way where he gets checked and gets screened. And when he passes through these gates, he can reach the king at the end to meet him and give him the message. So we need to build walls around our data or endpoint to secure the data and the endpoint, and create these choke points where we can screen and monitor who's coming and who's going from our city. And if we look onto the right side, it's a picture of gates, and these gates are marked with direction. So it's also a representation of who's coming and exiting. A modern city usually have tolls to tell you who's coming and who's going. So how is this done from analogy to reality? This is a picture of an industrial network model, where at the bottom side of it we have the actual in-field devices, the machinery network, and it could be a fleet of devices or fleet of vehicles as well. In the middle, it's an industrialized network, DMZ, or called demilitarized zone. And demilitarized zone, for people who hear about it for the first time, it's a way to separate your internal devices that is exposed to an external network. So an example here for an external network could be an internet, or it could be some external network for vendor or provider mobile network. It can be any external network that you deem untrustworthy. And the industrial enterprise zone, it have usually fleet management, it could have fleet endpoint controllers, it could have manufacturing execution system. And on top, we have enterprise networks, so usually these are devices for business management and logistics. So what we note from this picture is we have multiple zones where we create layers of zones, and to move between zones you have to go through the green parts, which is a conduit or a secure choke point for the city. So if we look at it, it's a picture of a city, but represented as a network. So each of these choke points that the data have to pass through, it have to have a good conduit to decide if this data should move or not. And the way we do this is we use principles like authorization, authentication, integrity check. We also could encrypt our data so it's private when it moves between these zones. So if we look on the first service, for example, it's authorized, so it means it's satisfied the metrics I just said: authorization, authentication, integrity, and encryption. If we look at the service 2, it tried to reach in-field devices, but it got denied because it didn't really satisfy these conditions. And this is a good concept that if a service 2 gets exploited, it can't just jump to the next zone, because it will get denied as these choke points that we designed for our system. So these are exactly the good definition of a good conduit: authentication, authorization, confidentiality, integrity. So authentication means you verify who's connecting with who, and they need to show a proof for it. And usually in internet, for example, this proof is usually a certificate for your website. So website has to show you a certificate and you check it against the certificate authority. Similar to if you have a driving license and the police checks it and knows it's produced by this country, so it must be true. Authorization is, you say if a service is privileged enough to reach your in-field factory machine or not. So you say a person is allowed to reach this machinery because he works with it, but another person, he has no business reaching this machine. Confidentiality means that your communication between service to in-field device, it's private. In reality, it means it's encrypted. So encrypted data is garbled. It's not a clear text that you can read anymore. And only the sender and the receiver can decrypt the data and look at it and understand it. Integrity means if the data passing through the conduit is getting sniffed or checked, it cannot also get tampered and manipulated on the way. So you also check that the data was correct passing through your city or your conduits. Availability means that your resource is available. So if you have an endpoint between service 1 and service 2, you couldn't really bombard the service with so many requests that it becomes unavailable anymore because it can't process all these requests anymore. So you have to also think about that resources need to be available. For your server, it could also mean that if you encrypt your database with keys, you can take backups of them to make sure they are not really, if the keys gets lost, for example, your data is backed up and you can retrieve them again. The last concept is freshness, which means that whatever crypto or keys you use to secure your data through the choke points, it should also be rotated. So if one of them gets discovered out, it gets rotated. So it's not very easy to try to brute force it for years, and it will get rotated before that. So how do we design this segmented SETI that we just looked at? You need first to define your business functions or assets in the project, which can be data or endpoint. You need to define what is criticality or exposure of them, who can reach them, and who manages them. And based on that, you need to split your system into zones, or that the data can flow from and to. And these splits can be simple, as you could do it like internal or external network. You could simplify it as I have a diagnostic area that requires a high privilege or high authentication through the choke points to change your device. You could also look at it as server and backend. You could split also if you have a very high safety critical or mission critical asset in a water treatment plant, or in automotive, for example, if you have a drivetrain or a braking system. You don't want to get the system hacked and suddenly they break the vehicle on the highway. So you can decide a zone based on characteristics of a risk level of the assets inside it. And you think about these zones like this. Components inside the zone could talk to each other, but they are on a similar risk level. But if you try to go outside this zone, you have to go through a secure conduit, a secure choke points that you can examine and apply the concepts that we talked about: authorization, authentication, encryption, and integrity. When you create these zones, you also need to have another Excel sheet where you say, I have a source zone, I have a destination zone, who's going to talk, which assets are allowed to talk between the zones, what ports they're going to use, what protocols are they going to talk, what is the direction where this data will flow, and why it is really needed to flow. Maybe it could just stay inside, and who owns this data that's moving through. Anything else, it should be really denied and should not move between the zones. And for startups, you shouldn't really complicate this. You should have 2 or 4 zones max, and you should really try to keep it down until you reach a product maturity level. Then you can look into something called microsegmentation, where you can break the zones to subzones as well. But demilitarized zone is a very simple to do in a project today. It's not really hard. Your router at home actually tried to do this demilitarized zone with abstracting your IP address with network translation table, or trying to apply firewall at home. So this is a simple how to do a demilitarized zone, for example, for your setup at home. So what is really our mechanism to do this isolation between network zones? You could use the switches, you could use network interface cards, you could even separate them based on router and switches, and at each physical device that you separate on, you could apply a choke point mechanism with all the security conduits that you could examine and authenticate the traffic in. And one easy way to do this is to do something called virtual LAN or virtual networks. So you take your physical network and you start dividing it virtually or logically based on a group of devices or a group of endpoints. So if you have an Ethernet or a Wi-Fi endpoint, for example, you could divide it into multiple virtual devices, and each virtual device will have an assigned IP address. And in a way, they act as an entry point or a gates inside your high walled zone. The other ways to enforce this is to use a firewall. So a firewall basically acts as a packet filtering. So you look into what is the traffic gonna flow on this virtual LANs or virtual endpoints for the LAN, and you decide if the traffic is allowed to move or not. And another way also is to not go through the same, if you use cellular network, you could use private APN. So that means you ask your mobile network provider to give you a special access point for your cellular data, and instead of going same as data as everyone goes through the mobile network. So VLANs or virtual LANs, they work at layer 2, and they basically work like this in the protocol. You add a VLAN ID that identify which virtual network this traffic belongs to, and also which priority can it have when it moves between the network. Devices in different VLANs, they don't really see each other. So an example for this at your home, if you have a guest Wi-Fi at home, you can't really see your the rest of your home network. They can't really see if you have a home theater cinema is exposed on the network, or they can't really ping your computer because they would be on a virtual network. So most routers actually today support virtual LANs. But you could leverage this also same concept for IoT. You can group IoT devices, let's say every 100 in-field device, you can group them in a virtual LAN zone, and that can help you, for example, mitigate if one of these devices are exposed, it doesn't expose all the fleet, it exposes the basket that your eggs in. Gothenburg is the city of automotive, so I thought about an automotive concept here for VLANs. So you could group also an ECUs in the truck. So a truck is like a distributed computers and a distributed IoT devices, you can say. And you could group ECUs in the truck and also their own group of virtual Ethernet. And you could basically say a browser in the infotainment system, it cannot see the drivetrain anymore. So if you have a vulnerability in a Chrome or Chromium project, it can't really be leaked into a drivetrain where it controls the engine now and it controls the brakes now, because it's totally a different VLAN network. So devices have to move between VLANs, they need a routing, explicit routing rule and explicit checks to check this between the network. So in Linux, you can basically declare a virtual VLANs using system network D. So you can define your network. And you can split, this is an example of how you split your Ethernet into virtual networks. If you use microcontrollers, you have Zephyr RTOS, and that's a really popular RTOS nowadays. It's under the same Linux foundation, and it's really, really rich in features. And it uses similar concepts as Linux, where you have kernel configs, and you can define a kernel configs that you can also split your VLAN your Ethernet into different VLANs. An example for this, you could have a VLAN for controllability or updates. You could have a VLAN for telemetry. So this VLAN, it can also give us other things. So you could, besides prioritizing which packets have high prio over which, you could also look into data rate constraining using a packet filtering. So you can say this VLAN is allowed only into 10 megabytes per second, because the device would never generate more traffic than this. Or you can say this VLAN is allowed only to a certain protocol like HTTPS, but it's not allowed to be pinged, so you can get ICMP protocol, for example. you could do something like a stateful tracking, so you can look into if the connection had been initiated or not, is this related to traffic or not. So you can enforce a lot of controllability and different security policies on different VLANs. So packet filtering is one way of doing a firewall. And basically you look into a source and a destination of a packet and which port is it trying to reach. And you say, is this packet allowed to reach my system or not? Is it allowed to reach the cloud or not? Did it come externally from a known source that I know of or not? And the way that you do packet filtering for your device, that you guard your wall, you guard your secure wall, you can basically say everything is dropped unless I explicitly say this source and destination on an Ethernet packet or a VLAN packet is allowed. Packet filtering in Linux, it's already supported in the kernel. There's a netfilter kernel module, and that netfilter kernel module can be easily instrumented from user space using NF tables. You can declare your rule set in an expressive way, and which declares which traffic is allowed to pass where, and the kernel will go and execute this for you. This is a picture of the networking stack in Linux, and the way that NF tables work or netfilter work is that every part of the networking stack, it has hooks. So if you want to go through ingress or egress of a packet in the network stack, routing, forwarding, bridging, everything of it have hooks. And you could define a network firewall or a packet filtering rule for it to decide if this packet is supposed to move to the next step in the network stack or not. So you can apply a very detailed traffic policy if you like to. Packet filtering also can be stateful, so that means that you can decide if your MQTT or if your lightweight M2M or if your HTTPS connection has been established or not, and who's allowed to establish the connection. Otherwise, you're allowed to drop the connection. If no connection is established and the device is trying to access an endpoint, you can say, no, you should establish the connection first. You're not following the right steps of the protocol, so you can enforce the protocol transitions as well. So this is a very powerful way also to inspect the traffic before the app intervene, or before the packets get the app even to decide on. You could also use packet filtering for forensics, so you could log and mark the packets, and you could look into what packets are dropped. And it's very powerful in case your system gets attacked to see what IP is attacking your system, where is the source coming from. And sometimes it's also good to catch developers who is not following the right networking protocol or networking programming, trying to use random ports and random IP address in the system. So it's a very, very useful way to enforce a system architecture constraint, packets coming in and packets coming out of your system. And Zephyr RTOS also supports packet filtering, but it's much more lightweight. It's mostly stateless, meaning it only checks source, destination, and port. It doesn't really track states much, but it's a good start for a microcontroller. Another way to secure the traffic is to use VPN or IPsec, which means that you encrypt the data from the network interface to another network interface. So if you have two devices, you could try to apply VPN. Probably all of you heard about VPN. If you want to do something on the internet and you don't want your internet service provider to check your traffic, you use VPN because it encrypts the traffic. So VPN is a network layer 3 encryption or protection, and it works exactly the same. It authenticates first the device that it wants to create a tunnel toward to, and once it's authenticated, it agrees with it on a crypto proposal to use, what language of cryptos does the other device speaks, And from there, it builds in the kernel, it builds a security association that's supposed to take any traffic going through the network, encrypt it or decrypt it based on the keys that has been negotiated with the other peer that you authenticate. Zephyr RTOS support WireGuard. It's not a true IPsec, it's a VPN, which means it's much more simpler in feature. You don't really negotiate, you have to configure it statically between both peers based on knowing the exact cryptos and exact shared keys or exact shared secrets. And it just has been added actually in Zephyr, so now you can encrypt all the traffic going through the network all the way to the other peer, which could be your cloud backend, for example. Another mechanism to protect the applications is to use TLS, and Internet today runs on TLS. TLS basically end-to-end application encryption. So when applications try to open a network socket in Linux, it uses a TLS crypto to encrypt the data all the way until the cloud, your Kubernetes pod, service running in Kubernetes pod is allowed to decrypt or look into this data. So mainly TLS secures an endpoint API, so it doesn't really secure all the traffic in the network. So if you have an application that uses TLS, it doesn't mean the rest of the applications on the system uses TLS. So that's a different distinguish between IPsec and TLS. IPsec secure all the traffic passing on a endpoint, on a network endpoint, like a VLAN or an actual LAN, but TLS secures the data from an application process perspective, or a certain socket. And the TLS is now supported in HTTPS, MQTT, lightweight MTM, and many other projects. Like I said, the Internet today run, if you look into HTTPS, the lock icon on the top left, it marks this site as safe, which means it's used TLS crypto or TLS certificates. Linux supports TLS via OpenSSL or GNU TLS libraries, and Zephyr supported using embed TLS. And if you use embed TLS in Zephyr, you can use it with all your favorite IoT protocols like MQTT, HTTP, REST, APIs, lightweight MTM, all of them you can use with TLS. The final security mechanism is called MACsec. So a MACsec actually is a link layer protection, similar to your Wi-Fi password at home that runs over WPA. It secures and encrypts all the traffic passing through the physical wire of the Ethernet. So you have to authenticate the device all the way to the next link layer, which could be your router or your switch. And it also works similar fashion way that a secure conduit will have to use. It will have to authenticate, encrypt, and check for integrity. MACsec is really popular. Use is if you don't really trust a tampering of an Ethernet cable, so you think someone could just pull the Ethernet cable and try to sniff the traffic. So MACsec really prevents that. So what is really the dependencies for the secure conduit? We mentioned they use authentication, encryption, integrity. So what they actually need to do this? They need a public key and private key or pre-shared keys. They need certain passwords or keys stored on the device in a secure place. And these are topic also for another session, but I just want to declare it as a dependency. To be able to have a secure conduit, you need this type of dependency. So you need to have a way to get certificates or keys to your device. You need to plan for rotation of these keys or certificates. You need a mechanism for logistics to distribute it in the factory for your devices. And you need also a crypto cipher suite to use with the device. And finally, when these devices talk to each other, they need to validate if the certificates have had a good issue date, are they expired or not. So devices also need to have time provision on them or obtain it from a secure source. So NTP protocol in Linux is, or from Crony, for example, is a good way. Or you can use NTS in Crony, Network Time Secure, and it also works in similar fashion. You authenticate your peer source or the master of time source, could be a server, and you trust the time that it gives you based on a certificate or a key. So when to use which cybersecurity mechanism of those. So like I said, TLS is an app security, end-to-end app security. So you use it with the apps. IPsec is for all the traffic passing through a certain network interface. And MACsec is to protect the wire. So you could actually use all three of them if you determine that a certain data or asset is extremely dangerous to get exposed, and I need every security out there to use it. Or you can choose a combo of TLS and IPsec, for example, or you can choose a certain mechanism for each part of the system. So if you look into this diagram, it shows different security mechanisms at different level of the OSI graph. So this is Open Systems Interconnect stack, and it shows the networking stack, how it works from the perspective of network. So each packet path or each data path from application to physical, it adds an extra info for it. So you can find MACsec at the bottom because it protects the data before they go on the wire. IPsec on this graph because it protects the data from a certain network interface. And TLS because it covers the transport that the application opens, so that's the socket. And the application data that the application uses. So the more that we use a certain mechanism up, the more it becomes more granular. Each app could have its own key, own certificate, own crypto, own algorithm. And at the bottom, it becomes of a catch-all crypto protection mechanism. So that also gives you a way to think how should you encrypt your data flowing between a zone 1 and a zone 2, which can be your app or backend in the cloud. This is the final use case. I see I'm running out of time. So this is a smart EV charging system. So it's a design of a system for charging vehicles. So imagine on the street you have a charging rack for vehicles, and each rack have 10 ports with 10 microcontrollers, and each microcontroller can charge a vehicle. And the rack is connected to a gateway, and the gateway is connected to our cloud through a cellular connectivity. And a user can use a mobile app to start charging or stop charging of his vehicle. So the design here is to think a little bit how can we protect the data, moving from the microcontrollers on the left to going through the gateway all the way to cloud and all the way to the mobile companion app. So if it's up to me really how to design it, I would split the devices or the microcontrollers that control the charging port into different VLANs. So I would use a VLAN for charger management, so that's to stop or start charging. I would create also a user network that can only access some charging management through VLAN 20. And I would create a different VLAN for power metering because that's sensitive data where you can change the billing. And I would create another network, logical virtual network for OTA or maintenance. And that's the most high security network. And I would also use MACsec to secure if these microcontrollers is connected by a Ethernet to the charger gateway. I would use MACsec to secure it. And a charger gateway can be like a central ECU or a router that connects to internet via SIM card. So I would want to secure the Ethernet cables connected to it. And if the connection to the cloud goes through mobile network operator, I wouldn't really trust them because the traffic is going through internet, more or less. So for that, I would use IPsec or VPN to encrypt all traffic going to the cloud. And I would also use TLS for endpoints, so power metering or charge management, that also as an application implemented on the microcontroller using HTTP or MQTT, it also should use TLS. And from cloud backend to mobile app, I would also use TLS to encrypt the Android application connectivity to the cloud. So that means that all the communication from microcontroller would be encrypted on the wire to the gateway. It's also encrypted to the cloud via TLS, and it's going through IPsec or VPN tunnel from gateway to TLS. So there is no exposure on the internet, and this should be a secure chain to secure the data generated in field all the way to make it to the cloud. So summary, what we have actually learned today is products are highly connected more than ever. They have high attack surface, and it's important to secure or design cybersecurity for networking and data flow from day one in the project. So it has a good foundation that is woven into the project, and you thought about the network design of your product and your data from day one, so you don't get surprised at the end of the project how much cybersecurity work you have to do. And that you have a really great FOSS tools in Linux and Zephyrs to use VLANs or packet filtering or VPN and IPsec or TLS or MACsec. So yeah, so that's all. So thank you for listening.
Yeah, 1 or 2 minutes for Q&A. If anyone wants to share.
Hi, when already spending the resources on TLS, why not go to MTLS?
But it's a very similar. It's a very similar. Doesn't really work. Or maybe I have to shut. It's very similar. You still need to go through authentication, encryption, and integrity, right?
Yes, but it's trust. You can do selective trust.
Okay, maybe you can teach me something that I don't know. You can share with us.
Yeah, sure.
Yeah, so I see like a lot of Linux and Zephyr OS, but there are quite a few other operating systems, for example, FreeRTOS, that, for example, doesn't have IP tables and VLANs. How would you approach that? Because like with the CRA Act coming and knocking at the door, like there are some devices that use that. Like, what would you recommend, for example? Use Linux.
Yeah. But does FreeRTOS support securing the data for the apps end to end? I mean, you have to analyze it from a Tara perspective. You have to see if using one mechanism like TLS is enough or not. If not, I would say the second level is you need to have an abstract gateway or an extra hardware to create this isolation if it's not physically possible. And you need to create the choke point on that extra hardware that could be a gateway or a switch or a router to the rest of the network if that's not possible. Thanks. Yeah. And this is the reason that I say you should consider cybersecurity when you architect the product day one, because then you could think you can bring up these questions really, really good.
Thank you very much. That's all the time we have for today. Please catch him after the talk. Thank you very much.